So collisions happen in hash tables as we are trying to map a huge space of application keys in a small array. But there are ways to solve it, and one of the most common ways is called chaining. In this video, we go in depth about collisions in hash tables, resolve them through chaining, explore some really granular details that would help us squeeze the best performance out of our implementation, and most importantly, look at a different data structure to implement it. But before we move forward, I'd like to talk to you about a course on system design that I've been running for over a year now. The course is a cohort-based course, which means I won't be rambling a solution and it will not be a monologue. Instead, a small focused group of 50-60 engineers every cohort will be brainstorming systems and designing it together. This way, we build a solid system and learn from each other's experiences. The course to date is enrolled by 600 plus engineers spanning 9 cohorts and 10 countries. Engineers from companies like Google, Microsoft, GitHub, Slack, Facebook, Tesla, Yelp, Flipkart, Dream11 and many more have taken this course and have some wonderful things to say. The coolest part about the course is the depth we go into and the breadth we cover. We cover topics ranging from real-time text communication for Slack to designing our own toy load balancer to ClickBuzz's live text commentary to doing impressions counting at scale for any advertisement business. In all, we would cover roughly 28 questions, and the detailed curriculum split week by week can be found on the course page, which is linked in the description down below. So if you're looking to learn system design from the first principles, you will love this course. I have 2 offerings for you. The first one is the live cohort based course, which you see on the left side, and the second one is the recorded course, which you can see on the right side. The live cohort based course happens every 2 months and it will go on for 8 weeks, while the recorded course contains the recordings from one of the past cohorts as is. If you are in a hurry and want to binge learn system design, I would highly recommend you going for the recorded one. Otherwise, the live cohort is where you can participate and discuss things live with me and the entire cohort and amplify your learnings. The decision is totally up to you. The course details, prerequisites, testimonials can be found on the course page arpitbhayani.me/masterclass, and I would highly recommend you to check that out. I put the link of the course in the description down below. So if you are interested to learn system design, go for it. Check out the link in the description down below, and I hope to see you in my next cohort. So conflicts are inevitable as we are trying to map a huge space of application keys onto a small array of limited size. So why does this happen? This happens because we are passing our key through a hash function which spits out a hash value, right? And there are chances that multiple keys when passed through that hash function would spit out the exact same hash key, which means that both of them are hashed to the same location, which means they have to occupy that same slot. So now, because there is a collision, now what could happen is if we are not handling collisions, the second value that is put in your array would replace the first one, which is bad because which makes your database or which makes your hash table lossy, which means if you inserted a particular key, then you are reinserting it. If both of them hash to the same location, the first one would be overwritten. Right? And you don't want that to happen because your user trusted you with its data and you don't want it to be deleted. So how do we solve it? There are 2 classical ways of achieving it. The first one is called chaining. The second one is called open addressing. In this video, we'll be focusing on chaining. Right? What is the core idea? The core idea of chaining is that we put the colliding keys in a data structure and hold them well. For example, if 2 keys are slotted in the same slot of an array, instead of one overwriting the other, we would use an auxiliary data structure in which we can accommodate both the keys hashed to the same slot. Right? And one of the most common implementation of this is with linked list, right? And which is why it got its name called chaining, because it resembles a chain. Right? So a quick gist of the idea is we would form a chain of keys that are hashed to the same slot, right? For example, in index 1, if I have 2 keys which are hashed, your index 1 in the array would hold a linked list. And in that linked list, you would keep on adding as many keys as it gets hashed to that same index, right? Similarly, it would happen at every other index. So in case there is a collision, you are always adding the key to this linked list, right? And this is how chaining, like the idea of chaining is, right? Now we'll dive into smaller details of it to understand things that we would need to take care during implementation and get the best performance out of it, right? So what we'll first discuss? We'll first discuss chaining with linked list, right? So when we talk about when we want to chain and we are using linked list for it, there are three very important operations that we would need to support. First of all, adding a new key to this linked list. Second of all, check if the key is present in the linked list. And third of all, remove a key from the linked list, right? Because these are the three exact operations that happen on the hash table. So upon collision, you would need to add this thing to the linked list. You would need to check if the key is present in the hash table, and for that key, if it is going and basically hashing to a same slot which is held by a linked list, you need to check in the linked list if the key is present or not, and remove a list when hash table operation comes in to remove a key, which means you also have to remove it from the linked list, right? So these are the operations, these three key operations we need to support on linked list, right? So given that the simplest implementation is with singly linked list, you don't need to complicate it with doubly linked list or circular linked list. It does not make any sense. We'll go with the simplest approach, singly linked list, right? So now the array that we have, right? The array that we have, that array is nothing but an array of linked list, right? Where each slot of the array holds a head pointer to the linked list, right? So that whenever a key is hashed to that location, it is added to this particular linked list, right? And that is the entire role of this array, right? It is now, earlier it used to hold keys. We don't need that. Now it would hold the actual linked list because we have to support collisions, right? Okay. And each slot and each slot of the array contains a head to the point of the linked list, which looks like the standard definition of a struct. So what it would have is your array of a linked list, your array of linked list that you have, every slot is nothing but a structure called slot with struct node star head pointing to the head element of the linked list, right? And each node of the list, right, of the linked list that you have, it contains two things. It contains an actual key that it would store and the pointer to the next node, right? Now, why would we need to store actual key? So that we can do that comparison. We can do that comparison because let's say if apple and ant hash to the same location, we need to, and if someone says, hey, delete apple, you need to traverse to the linked list and identify apple and then delete it, right? So you would need to keep the void pointer key and a struct node next so that you can form your linked list there, right? So now let's see, with this concept in place, how hash table operations pan out. So let's say we start with the basic operations, adding a key. So adding a key to the linked list, let's say we have three keys, K1, K2, K3. And what do we have? We have an array of size 4, right? And because with the array is an array of linked list, each head pointer of the linked list, it points, it's basically set to null, which means there is nothing in it, right? So now what would we do? Let's say put K1, V1 came in, and let's say K1 hashed to index 2. So it would go to the index 2 and it would then your head pointer at index 2 of the array would start pointing to this new node, right? Let's say then then we got a put for K2 V2, which means insert key K2 with value V2. Let's say it got hashed at index 0. So it would go and sit at index 0 at the head of the linked list, right? And let's say we got a third put for K3, V3. When I got K3, V3, it got hashed at index 2. It would come to index 2 and it would find, hey, on index 2, the head pointer is already set. So key K3, V3 would go and sit at the tail of the linked list after key K1, V1. This way what would happen? We would form a very solid chain. We would form a very solid chain of the nodes whenever the collision happens, right? So the basic flow would be given a key and a value to be added, we pass the key through the hash function and get an index I. We create a new linked list node with K, V. We add it to the chain present at index I in the array, right? This is a basic add operation that would happen, right? But obviously that should not be just one way to implement it. There are multiple ways of implementation. Now, for example, given that you want to add a value to, or given that you would want to add a key to this linked list because there was a collision, if you want to add it to this linked list, where you can add it, right? So to make your insertions lightning fast, what you can do is you can always insert it at the head of the linked list, right? So whenever you got a key to be added to the hash table, you would hash it to a particular slot. In that, when you're adding it to the linked list, you are directly adding it to the head. So it's just head pointer manipulation, which is lightning fast order 1 operation. So you'll get very high write performance on your hash table, right? Second place is where you can do is you can always add your node to the tail of the linked list. Now you'd say, but adding to the tail of the linked list every time might require me to go through the array or through the linked list, right? Once you got the slot, you'd have to go through the linked list, go to the end of it and then add the node. No, that is one naive way to do it. But what you can also do is in your array, you can keep track of your tail pointer. If you can keep a track of which node is the last, your add insertion at the tail can also happen at order 1. Right, so it is also fast. So it's up to you. If you want to add it to the head, go for it. If you want to add it to the tail, go for it. Right? But there is a third approach, third implementation that you can do is, say you'd want to maintain an inherent order. For example, you are storing strings as a key, right? And let's say you have created 26 slots, A to Z. So A slot of the array would contain linked list of all the keys that starts with A, right? Now let's say, because strings are comparable, you might want to have a lexicographical order. If you want to have a lexicographical order, so then let's say you inserted ant. So it went and sit at the first place in the linked list. Then you added atom. But when you're trying to add atom after ant, you would see atom would come after ant. So you would have to traverse and then add atom at the end of the linked list because it comes after ant. And then let's say now it comes apple. So apple is after ant but before at, right? So given that is the case, you would have to iterate through the linked list, find the place that would be appropriate for this key to be slotted in the linked list, and that's where you would add it. So if you would want to maintain some sort order, whenever the collision happens, your insertion would need to be according to that, right? So 3 possible implementations of inserting in the linked list: always add it to the head, or always add it to the tail, or depending on the order, you would be adding it to the linked list. One caveat is, if you are by default adding it to the head, one small problem would come in. You might get duplicate keys in your collision. For example, if I added apple with value v1 and then I added apple with value v2, if you are blindly adding it to the head of the linked list, then what would happen is you would have 2 apples in the linked list. So it's up to your implementation on how you would want to do it. But depending on the kind of requirements you have, you can decide how do you want to slot it. But the worst case that you can definitely do is, for a given key, when you reach to the slot, see if the key is already present. If it is not present, then you add it to the list. Otherwise, whatever is present, you replace it to that node, right? So there are multiple ways to implement this, but it is up to you as an engineer on which approach do you want to pick. Right? Okay, now let's look at second operation, deleting a key. Now, how adding a key was straightforward. It was just about inserting it into the linked list. Deleting is also very straightforward. So let's say we delete it in a particular order. Let's say we first delete K2, then we delete K1, then we delete K3. Just to set the context, array is of size 4. So 0, 1, 2, 3. On slot 0, I have K2, V2. On slot 2, I have K1, V1 and K3, V3 in this order, right? So now how would we do delete? Delete operations is pretty simple. We reach the slot in order one time because given a key, we would pass it to the hash function, we would get the index. Once we got the index, we know which linked list are we targeting. Then we start iterating through the list node by node to find where node arrow key equal to K1, which means we'll identify the node where my key is present. While we are iterating, we would have to keep track of a previous node, right? Once we reach the node that we intend to delete, we would have to adjust the pointer. So previous node would point to the next node and we would delete the intended node, right? So one key thing to note over here when you're implementing it with linked list, ensure that your pointers are handled and adjusted well, because this is a very common reason why segmentation faults or some error happens, like because it's very bug prone, right? So ensure that you are doing it very well. But deletes are also straightforward. You just need to keep track of a previous node while you are deleting it, right? Third is looking up a key. Now this is very similar to delete operation. So here what we do is, let's say we would want to get a particular key from the hash table. So what we do, given a key, we pass it to the hash function, get an index, go to that particular slot in the array, start traversing through the linked list node by node until we find the node that holds our key, right? So now this means that order 1, we would reach the slot, but then it would be linear scan on the linked list to find the node that interests us, right? So if you have a very high collision rate, where let's say if one of the linked list grown out to be really big, let's say 100 elements, 200 elements, you have to linearly iterate through it to spot your key. So if your collisions are less, this approach works best, but prepare for the worst case where your linked list might grow to be very big. So it's almost like a linear scan, right? So always be wary of the fact then when you grow or when there is a very high collision on one of the index, it's the time when you would want to resize your array, which means from 4 you would go to 8, right? So just keep that in mind whenever you are implementing it, and which is what we would be definitely be covering in the upcoming videos on how do we resize this array, how do we decide when to do it, and a lot of details around that, right? But although linked list is the most common ways of implementation, what you can clearly see is if you have a very large collision rate, right, where one of the linked lists is going out to be very big, it would affect our lookup times, and date and hash tables are meant to be efficient at lookups. So you order when you reach to the slot, but after that you are doing this linear scan. Can you make it better, right? So that is where instead of using linked list, you can use other data structure. For example, you can use a tree, a self-balancing binary tree instead of a linked list. So now your array is an array of self-balancing binary trees. And when you are inserting, you would insert in this tree. When you are deleting, you would delete from this tree. When you are looking up, you look up into this tree. And this would give you good performance. Like not with respect to inserts. Inserts are costly, right? Inserts would be log n. Your deletes would be log n. But your lookups would also be log n. And here n is the depth of the tree. So typically it's order h, right? So where if h is the average height of a self-balancing binary tree across your array, this would give you the complexity of that. So now where would you use this? Where would you use tree for chaining instead of using linked list? You would use it where you are having very high collision rates, number one, and you cannot resize your array to a bigger number, which means that let's say I have 4 elements in my array and due to some implementation reason, I cannot expand it to 8. And I want to keep my hash table array to be of very small length. When I want to do that, which means that if I'm inserting a large number of keys, a lot of them would collide to the same slot, right? And it might be possible that I might have thousands of keys, given that I have 4 slots. Let's say I'm adding 4,000 keys. So each slot on an average would have 1,000 keys, right? And now when I'm doing a get, imagine every time doing a get, if I was implementing it with a linked list, I would have to do a linear traversal of it. But with trees, what I can get is, I can go to that slot and do a log and search in the tree because it is self-balancing binary tree. I can do a log and search and return the value, right? So my lookups will be much faster. So we can use any self-balancing binary search tree, or not really binary, but any search tree when we are expecting a large number of collisions, then, and large as in hundreds if not thousands at least, and then you can go for this kind of approach. So linked list is not the only way of implementing chaining. You can also use something like a self-balancing binary tree, but understand the limitations of it, right? Your insertions would be a little costly, your deletions would be a little costly, but your lookups would be faster. But you only do that when your number of slots are very limited and you are not allowed to expand further. That's when you might want to go for a self-balancing binary tree instead of a linked list. And this is all about chaining. This is all about chaining, its implementation with linked list, its implementation with trees. And that's all what I wanted to cover this one, right? So great. Again, that's it for this one. If you guys like this video, give this video a thumbs up. If you guys like the channel, give this channel a sub. I post 3 in-depth engineering videos every week and I'll see you in the next one. Thanks a ton.